Hello, everyone. It's really great to be here today, here to defend the 3D user interfaces from 2D data visualization that we have heard about in the last talk. So, my name is Madlaina Kalunder, and I am a game designer and a software developer. My mission is to make 3D content accessible to everyone, especially for developers, because as you will find out, it's not such an easy task for people who are not in the 3D space to actually start understanding what is necessary or what are the necessary components to get started and to really make good 3D applications. So currently I'm working at the FHNW Institute. It's a university of applied science in Switzerland, and our institute is for interactive technologies. I'm there as a research associate focusing on spatial computing. And what that means, we will actually find out later in the talk. I'm also an invited expert in the immersive web working group from the W3C, which I would also like to briefly focus on the talk today, because it will be relevant for all you web developers to see where the web platform is heading concerning 3D applications. I am based in Switzerland, and I really like games. That's why I studied game design. I also like to play games with friends, but at the moment there's just no time for it. I also really do a lot of community work in Switzerland and internationally. I like to travel, to be creative, to play music and many other things. So get in touch if you want to after the talk, on Twitter or on LinkedIn. So as Richard has also been talking about before, I would like to start this talk with explaining the title, Flatland, Beyond Flatland, the rise of the 3D user interfaces. So Flatland is actually a satirical novella about the Victorian age, also in the UK. And it has been written by Edwin Abbott in 1884. And the interesting thing is that it actually focuses on talking about a fictional two-dimensional world. It's also a social satire about the Victorian age, but at the same time it's really interesting to see what kind of problems you face when you take away one dimension and how to imagine how you could actually live in such a world. So here, for example, you see a diagram of a square's house. A square is usually a man, not of high class, just a regular person in this space. And you can see that it's a pentagon-shaped, not a pentagon, polygonal-shaped house. And we have two entrances. One is here. It's really small for the women. And then there is one over there for the men. And the reason is because the men are actually polygonal-shaped and women are lines. So they need less space to go into the door. But also at the same time, it's an orientation problem because the men actually have to go from this side, so from the west, to enter the house, and the women from the other side, because otherwise they would not find their ways. So this allegory I'm using to show what kind of problems we face when we try to imagine a different world. And actually, in this book, this square is trying to explain the reader this world, and the reader is a so-called Spacelander. I will get to that a bit later. 3D user interfaces. When I first started doing more research about 3D user interfaces, it was really hard to imagine what that actually means. The biggest problem is that we are used to talking about 2D user interfaces, and it's mostly limited to graphical interface elements such as buttons, diagrams, labels, etc. And the interaction that we program or develop on top of these user interfaces, they are a different category. In 3D, however, three-dimensional user interfaces let users interact with virtual objects, environments, or information using 3D direct input in the physical or in the virtual space. That means a 3D user interface can be completely virtual, so we can just do it on a 2D screen, where it's more also graphical elements and 3D objects that we interact with, or it can also actually extend to us giving actual three-dimensional input, which is what we want to talk about today. And the reason why this is important is that we are entering an age of ubiquitous computing. So computers are actually expanding into the real world and are not confined to one single screen anymore. This is called spatial computing. So the machines are no longer contained to a single location, but instead can occupy different parts of space around us. So with this very loose definition, we can already describe so many different varieties of 3D user interfaces. So I have tried to give a very small sample of what that could mean. On the top left, we have a Microsoft HoloLens application, where there is actually one moderator leading other people through looking at this model of a surgical room, I think. Then we also have 3D user interfaces that are actually just a two-dimensional representation, but they are in the 3D space, they are located on a specific element of this object we want to describe. So in this case, it's this car, it's the wheel of the car that we want to give more information to the user. Then it's also augmented reality applications, such as Pokemon Go. It's probably the most famous example, where we actually use the space that we are standing now, so GPS-located spaces, to determine what we see on the screen. But on the screen itself, there is not much 3D interaction going on. But it matters where we are standing, because that's what determines which Pokemons we can catch. Then this is an example for an actual gesture device, so that's the leap motion. I really like this example because it shows how the physical space and the virtual space come together. Another really important field of application is telerobotics. So we have some operator that is wearing a bodysuit or a full device or just a robotic arm that he can control to actually control a robot or a surgical instrument remotely. And that can be close by, or it could actually be over a big space, or it could also be that it scales down the interaction. So we do a big interaction, but inside of somebody's body or in a surgical operation, that movement is being scaled. Sorry. Try to make this less nosy. Okay. So why 3D interfaces? We have heard before that 3D data visualization, for example, is not always the best choice because it's hard for the user to actually see, and there is data that is being obscured. But in general, 3D interaction is relevant to real-world tasks. And I would like you to today go out of this talk with some ideas on when 3D is actually useful and to determine when you should use it. The technology is becoming mature. We are now already past the hype phase, Now we're starting to get to see really what we can actually do with these technologies. In general, 3D interaction is difficult, but at the same time, it's the most natural thing that we have in our lives. Current 3D UIs are mostly very straightforward and lack usability, so there is a lot of research that needs to be done. And it's also an area that is ripe for future work. It's contradicting to the traditional interactive systems. That's why I work in this field, because it's very interesting to be a part of this. So what is Spaceland? Abbott has also in his book thought about what other dimensions could look like in this kind of social societies, and he was talking about point land, where there is no dimension, line land, one dimension, flat land we have heard about before, and then 3 dimensions, Spaceland. He even went so far to think about how this 4th dimension world could look like and how things are organized there, so I recommend to read. But generally, we are living in Spaceland, everybody of us, and we have the right part of our brain to help us with spatial intelligence. Actually, that is the primary function of the right brain. So it helps us with actually solving 3-dimensional tasks. And I'm saying this because it's really important to know that at the moment, most of the applications we use, we completely ignore this fact that we are actually spatial beings and that we have a skill that is maybe really hidden. So the spatial intelligence can help us solve puzzles, understanding maps, understanding the world around us, helps us in construction and engineering. And from a psychological standpoint, every one of us has a spatial map or has his own mental model of the world. This means how you as a person understand the world around you is very different from other people. You associate different ideas to different parts of the room or the rooms around you. You might know some spaces better than others. And this can help you with solving these puzzles. So why Spaceland? There was a really cool 3D game actually developed by the University of Washington, and it's called Folded. And it was a scientific video game about protein folding. The interesting part about this is through mechanisms of 3D user interfaces and 3D understanding, but also gamification methods, this video game solved very, very important scientific problems through actually the masses. So through gamers who played this game, who had no domain knowledge about proteins, didn't understand what was actually the use of doing this, they were able to solve a task that machine learning wasn't able to do, and no one else was able to solve it, actually within, I think, a few months or weeks, I'm not sure. So by adding this additional dimension to our applications, we actually just also gain more space. That's the first thing. We now have things around us. We can place it anywhere we want, which also gives us a lot of problems later on. But we will get to that too. So we can think about solving complex 3-dimensional problems that is impossible to solve in 2D space. Actually, that has also been how the DNA model was created, because they were able to do it in 3D, which is something they weren't able to solve in two dimensions. And also traditional scientists have been trying to make 3D applications in the sense of more mechanical or manual work to understand what they were actually working on. Another really interesting part is scale and explore. So usually what we see at the moment, or what we think about when we talk of augmented reality, mixed reality, etc., is that we have a one-on-one world representation. But as you see in this folded example, we can also go into a really small space and explore this in a reality or in an alternate reality that we couldn't explore otherwise. The same goes for really large spaces. So we can actually think about leaving this Earth or going anywhere to understand other concepts better. So just a quick overview on what's spatial computing. It's not yet fixed, defined. From my understanding, we have these 4 categories of applications that we can go for. The first one is virtual experience in physical spaces. So we have, for example, mixed reality, virtual reality applications, simulations or games that are completely virtual, but me as a person with my body and my input, I am controlling this. So the physical space is still important. Then we have virtual experiences in virtual space. That means we have, for example, an assistant on our phone that knows that we are now in Minsk. And it tries to help us navigate through Minsk, but it never comes to the physical world. It's a digital helper tool. Then physical experiences in physical space. So we try to understand the world, or we have autonomous vehicles that actually make their own digital model of the world, and they try to navigate through it. So that gives us also problems on how these machines should actually interact with the physical space, with other machines, and with humans. Then the last one is physical experiences in the virtual space. So there we actually have the teleoperations, so we have a physical control that does something in a virtual space. So I want to give a little bit more of understanding what this all could mean. What is a physical input in a virtual space is, for example, these buttons that I physically have to press to do something in a virtual space. Or I'm completely in the virtual space, but I use my own body to do something. It's just an example. How do we actually interact with this virtual space through our physical space? So this is the part of 3D user interfaces where it gets really interesting, because we have a lot of different devices that we need to understand, but we also need to understand what they are good for and when we should use them. So as a bit of overview, we have spatial controllers. This is what you actually know from the VR headsets, from AR headsets, or what's coming up now. We have a lot of variety in there. We have different degrees of freedom. That means how can you actually, in what degrees can you move the controller, and how does it actually track you? So the highest one is 6 degrees of freedom, which means I can walk back and forth, sideways, I can go up and down. These are 3 degrees of freedom. And I can pitch my head, roll it, and turn it. That's the other 3 degrees of freedom. 1 degree of freedom would be, for example, a button, because I can only press it in one direction. Then we also see coming up a lot of research and a lot of interest in actual haptic interfaces. Haptics is something that is a bit hard to understand, but if you have a smartphone, for example, and you press on the touch screen and you get a little vibration back, that's what's haptics. So it's something that gives you some sense of touch back. And there Haptics, we will also get into a bit more later to understand really what it could be. But we have 3D motion tracking, 3D force feedback, so the application can actually stop me from going further. And we have tactile displays. That's, for example, your smartphone giving you a feedback, even though it doesn't move any mechanical parts. Then what we also see is gesture tracking. That's where, for example, this Leap Motion product comes in, but also the Microsoft HoloLens is doing gesture tracking. There is a big margin of error that we hope that will be resolved with the future development. What we also see is full body tracking, so we actually have Kinects or game systems or complete bodysuits that can actually track your pose or multiple people's pose in a room. That gets interesting if you start to really explore the room and have different spaces where people can interact with some digital application. Then telerobotics are very much high-end devices, so they can cost up to $3 million US dollars, let's say it like this, because these are surgical instruments that are used for very specific tasks and they have to be the most accurate. What we also have is a lot of cameras where you can actually develop your own 3D interaction or gesture tracking or whatever, because you get the camera data and the infrared camera data. And at the same time, you can use IoT to create your own spatial inputs. So, for example, you could place buttons everywhere in this room that people have to press, and you connect them to your own system. So this would be kind of a small visual representation of what these devices would look like. So that's the Leap Motion, Kinect, 3x connection is for 3D modeling, but we could use it for anything. There is actually this haptic device from MIT, I think, where they actually have a display that can mechanically move parts to go up and down to simulate this person's movement from distance. We have this is also a 3D input device because it's a head-up display from Microsoft HoloLens 2. And this is considered also a spatial input device because we use the head tracking and everything. And there is some 6 degrees of freedom controllers from Oculus. So the biggest question I usually get is, what are the design principles to actually do 3D applications? What do I do? Is there some standards that I can use for my problem? And the biggest issue is that with this variety of input devices and output devices that we actually have at the moment in this time where it's not clear which one will survive and which one won't, but also this very big variety of use cases that we can think about, there's actually no really established design principles today, but I will try to give you a little bit of an insight on what you could consider if you want to get into this space, or maybe if you are a consumer of these applications and you want to know why it's not good enough, so you can actually debug it. So what are good guidelines? Actually really determined by the set of input and output devices you are choosing. But also standardization, it's still the question, can it be done? But at the same time, it's also, do we want it to be done? The 3D spatial applications are usually very specific and also have specific needs. So we always try, and in our institute, we always try to follow human-centered design. So we actually do a lot of iterations with real users. We try to do eye tracking to see where they look at. We have real prototypes, not just paper prototypes, where we actually start to develop the application and develop it in an agile way. Richard also has been talking about metaphors, so I'm kind of taking a lot from his talk over. We are now at this transition stage where we don't know if are these spatial computing devices coming, are they going to be used in a daily life or not? I will leave that up to your opinion. But we are at this transition phase that we already had before when we transitioned from just text OS to actual graphical user interfaces. And what happened there is something that I really urge to also happen now, is to use metaphors that people understand, understand. Here we have the first, I think, Windows 95 user interface, and you see that all the buttons are actually three-dimensional, because that gives the user that has not seen this system before an idea on how this should be used. And over time, these metaphors were not used anymore, or not important anymore. So now we are actually in the 2D space, we are really in a flat design stage. And this approach is actually called skeuomorphic design. It's a pretty weird word, but it means that we use real-life things to actually simulate the user on how to use the things. And that could be icons, or it could actually be input widgets that are actually really just designed the way they are in real life. So now in 2D interface design, we are in a flat era more. But for 3D, it's actually maybe a good idea to go back to this, because it's also a transition phase. What we want to do is mimic function and appearance of real-world objects. And this is a really old design guideline, actually. And also Apple has been doing this between 2010 and 2012, where they try to put a lot of real-world textures into their applications, like wooden backgrounds, or they actually try to put all your books in a real bookshelf and stuff like that. How could this look in a 3D application? So this is a GIF or a GIF from Job Simulator, and that's actually a VR application where you can see that it's really just a simulation of the real world, and each object is behaving the way it should be. I will skip through this a little bit because I have explained a lot, and it's actually going faster the time than I thought it would. So, what do we have to consider? We talked a bit about user interface, how things should look in 3D space, but there is a really big variety that I cannot cover in this talk. But what about interaction techniques? We talked about all these spatial input devices, but how do we actually use them? So the classification suggests that we actually go and distinguish between interaction techniques for universal tasks, that are things you probably do in different applications, which are the ones that could be standardized. Interaction techniques for composite and application-specific tasks are something that have to be developed probably per application. Then we have 3D UI widgets and tools. This is actually how we communicate information to the user and how the user actually interacts with our application visually. We also have 3D interaction techniques using 2D devices. So if you think about a game, for example, a 3D game, that's also a spatial application, but we use keyboard and mouse to interact with it. So we have to make a translation from 2D to 3D. Or all the actual mobile AR applications also have this translation from 2D input to 3D input. The biggest challenge is to seamlessly integrate those diverse techniques into one application. And this we do mostly by trying to create natural user interfaces. And here we have Also a scale that shows how those interactions could actually be done. It's a scale from direct to abstract, and direct inputs are mostly physical interactions based on real-world experiences, simple and natural. And abstract interactions are higher-level interactions that you actually have to learn. You have to study them. You maybe have to read a manual or a tutorial to learn all these things. This was, for me, mostly noticeable with the HoloLens gestures. So one thing, they don't work very well or didn't work very well. But one of those was really intuitive, and the other one was not so much. I would like to give a short video on how this could look in a 2D game. So in this game, The Gallery, Episode 2, Heart of the Emberstone, you have a lot of 3D user interfaces. Actually, your whole backpack that you're using is modeled after a real backpack. So when you want to open it, you grab behind you, you pull it in front of you. But you can see that it's really, it's maybe hard to see because it's a bit laggy. But the backpack, we'll see it later, or you actually have a slot where you can throw in what you want, but then you also have a digital 2D UI that kind of shows you what you have inside. So it's a nice way of merging this. Yes, you see it here. So you actually really throw it in and you can take it out again. And also these books you saw, you really open them with a physical interaction. It's not just the pressing of a button. And then we have this really cool game that's a VR construction game. It's actually, there was a 2D version of it, Fantastic Contraption, where you physically, with 3D user interactions, but also 3D user interfaces, you kind of model your mechanical contraption and then you can let the physics play out. And the really nice thing about this is that there is really no 2D overlay in this game. Even the actual game menu was this little cat that has been in the picture just before. So it's actually a companion element, but it also has a function of a menu. And now there's really not much time left, so quickly go through some other design principles. Immersion, for me as an experienced or game designer, storytelling is really important. So in 3D space, this is now a virtual reality example. We have different types of elements, and two of those are the body-locked element, the world-locked element. So there is an element in the world that just stays there. But more importantly, we have diegetic UIs. So these are user interfaces that are actually integrated in the world. They are logical, they're subtle, you maybe don't know that they actually exist, and they can also be context sensitive, so they can change based on what you want to do. And the virtual companions that I talked about before is also a storytelling element that you can use to actually create a bond between you and the player or the person who is interacting. And those companions, they can have very different functionality. They can be very annoying. They can be super cute. They can be menus. They can also be cynical and give you wrong advice. They can act as a tutorial helper. It can show you the interaction you're supposed to do, etc. So there's a lot of really interesting variety. The last important factor before I would have to stop my presentation are human factors. If we extend to 3D space, but also in 2D applications, this is really important. There is no one person, there is no model of a human being. We are different, we grow up, we are children, we're older, we're middle-aged, we have less or more experience. So please consider human physiology and psychology, and also make sure your people are comfortable. So motion sickness in VR is the first thing that a lot of people experience. there's a lot of performance optimizations you can do to make your people less sick, because you don't want them to be sick. But also consider individual proportions. If I am in a VR application where I cannot move around, I can only reach objects in my arm's length. And we all have different arm's length. There's actually a suggested API for this as well, for like a self-reference for you, for the web. It's called GravVR API. That is really interesting approach as well. And also consider the context of your people. Where do they actually use the application? I think I don't have to say too much about that. But also consider what these human factors actually make you, what opportunities they give you. So you can actually give people access to worlds that maybe otherwise wouldn't be able to do that. And this is the last thing that I'm going to talk about. I have more, so come to me if you want to. I have also more cool demos. So multimodal interaction. Consider, we have all these devices. Consider using them and actually combining them. Especially in this age where we can also use speech input, or we can just combine things. There is really interesting ways of doing this. So let me just skip. Thank you very much for your attention.
Thank you.
You can find the slides here, and yes, please get in touch. Also, if you're skeptic about this.
So, questions, please.
Hi, thank you for your speech. I want to ask you a question about a problem of physical feedback.
Yeah.
Well, it seems like it's an easy thing. If we're talking about telerobotics, we have this, I don't know, tracking suit or some kind of controllers, and you just put actuators into it, and probably that's it, yes. But if we're talking about VR, right now it just feels strange. At the best, we have like vibration that sticks. So my question is, if, for instance, I want to to play a simulator game and click all the buttons in the cockpit of my plane, which technologies will be available in the nearest future to me to feel, to track my hands and to feel all that clicks, you know. Maybe, I don't know, some goals that will simulate that feelings with direct electrical impulses to your hands or something like this, I don't know. What's coming in the next few years?
I hope I understand the question right. Thank you for the question. So for me, it's not clear yet which system will actually be on a consumer grade level next, so which one will actually get the most developed that consumers are also accepting. That's a really hard judgment to do. But what I totally agree with is that specifically for virtual reality experiences, it's really important to actually have a representation of yourself, because that's one thing that I would have liked to cover as well in the end of my slides. But that's one thing that is the most important to make this virtual experience actually be real. So one thing is to just see myself, because the body, if you cover your eyes, you still know where your limbs are, where your hands are. This is called proprioception. And it's really important, because otherwise you cannot function. But in virtual reality, it's hard to, because you have the proprioception, so you know where you are, but you don't see this represented in the space. So I think this is one of the next problems that have to be solved, specifically in VR, because in AR it's not a problem since you have to see through this place. And also the next thing then is to actually have this haptic feedback. So haptics, the sense of touch is bidirectional, so you can actually touch a virtual object, feel its consistency, feel its surface texture, etc. But it can also influence you. So if you try to press it too hard, but it's a hard object, that your haptic device will stop you from being able to grab it. So these are the two stages, in my opinion, that have to be solved, specifically in VR, to actually make it usable. I don't know if I have... Yeah. I think we also have to stop soon, but I hope this answers your question a little bit. So it really has to become real, those realities, to make it also a long-term use possible. Yeah. I don't think we are there yet with any of them, but...
Thank you. So, any questions? No? Okay. Thank you.
Thank you very much.